Hi there. This video is going to walk through doing an average value or an expectation value calculation. We're actually going to use an example that comes into play when you are completing problem 4.7 in your homework assignment. So this will be one of the quantities that you will have to calculate on your journey to calculating the variance for the energy for a particle in a box. So we're going to show that the average energy for a particle in a state described by this wave function here, with the limits of x being between 0 and a, so essentially the same limits as our particle in a box. We want to show that the average energy for that state is 6h bar squared over ma squared. Okay, so what should jump out at you when you read this problem is we're looking for the average energy. Okay, and so when you see that, you should automatically know right away where to begin your work. So we know that the expression for calculating the average energy of a quantity is a standard expression. So if we want to calculate the average energy of this particular state, we denote that with our quantity, our observable quantity that we're looking for, and then these brackets around that just indicate that we're calculating the average value. Okay, so whenever you see this notation, that just means we're calculating an average, also known as an expectation value. Okay, so what average do we anticipate for this particular wave function? Okay, so we want the average energy, so that calculation is going to look like the integral of our complex conjugate of our wave function. We want to put our total energy operator in the middle, so that would be our Hamiltonian. And then we have our wave function again, times our differential volume element. So we're one dimension here, so that's just dx. And don't forget your limits. So here, right, you're given your limits in the problem, so we know our limits are 0 to a. Okay, so remember, this is your standard setup for any average value calculation. It doesn't matter what average value you're calculating, this is going to be the standard form, okay, where you've got your operator for that particular observable quantity that you're looking for. That gets sandwiched in the middle between your psi star and psi. Okay, so don't make the mistake of putting your operator out front here or out over here. Okay, it will make a difference in many of your calculations. Okay, so remember, some of our operators have derivatives in them, especially this one. So that will, the order that you set this equation up will be very important. Okay, so again, this is just an expression that you should commit to memory. Okay, this is never going to change. Always going to have this same setup. Operator sandwiched in the middle. Okay, so let's start plugging in our wave function and our operator and start evaluating. So integral from 0 to a. Alright, so we're going to put in our expression for a wave function that's given to us. Okay, so we have our expression from above. And then we want to put our operator next. So the Hamiltonian operator for our particle in a box, remember, we have no potential energy in this system, so it's just going to be our kinetic energy operator. So that's minus h bar squared over 2m d squared dx squared. And notice that I'm not bothering with the partial derivatives here because we're only working in one dimension, but down the road we will do our partial derivatives once we get more than one dimension coming into play. So just make a note of that. We don't need them right now. And then we put our wave function again after the operator. Okay, so this is just the initial setup for the expression that we want to evaluate to calculate that average energy for this particular particle in this particular state. Okay, so this looks pretty nasty. So let's start doing some evaluating. Hopefully things get a little bit more simplified for us. So the first thing that I'm going to recommend that you do is to evaluate. Everyone's going to have their own approach to doing this, so do whatever works for you. But I like to sort of expand these terms, take out all my constants, so get rid of all of these constants here, pull those out of your integral, and then I like to expand this before I take the derivative. I find it a little bit easier to get where I want to go that way. But again, that's just my personal preference. You can take other approaches to this, so just do whatever works for you. There's no one way to do these problems. I'm just showing you one example. Okay, so once you kind of simplify that a little bit, so again, pull out all your constants here, evaluate the derivative. Right, so remember this second derivative is going to act on this part of your wave function term where you have your x's. Okay, so take a minute to stop the video and do that part of the evaluation, and then we'll move on the next slide to working beyond that point. Okay, so this is where I ended up after doing all of that evaluating of the second derivative on that second part of the wave function. I pulled out all my constants, okay, and this is where I ended up. Hopefully you ended up someplace similar. You may have a slightly different form if you didn't choose to do the expansion here. Okay, that's fine. So I'm going to show you a couple ways to evaluate this integral from this point on. So there's a couple ways you can do it. One way is kind of old school, just brute force integration without using an integral table. Or there's a little bit of a shortcut if you have access to an integral table. You can cut that down a little bit. Okay, so the first method I will go through is no integral table method. So if you're just hanging out by the fire, calculating an average value, and you don't have access to your integral tables, you can keep going. It's not going to stop you. All right, so from here, what we will do is you can just, again, continue expanding. So just kind of factor all these through, okay? And we'll just kind of keep on trucking. All right, so we will have, again, our constant still out front. So those are going to stay there. And then we can just simplify our integrand. I don't know if you want to call this simplification, but we can rewrite our integrand a little bit. So you might pause the video at some point and see if you can get to where I'm going here. Okay, so what I've done here is just kind of expanded this term like we did over there, so getting another one of these, and then just multiplying everything out, and then grouping all of our like terms together. So when all is said and done, we should end up with this integrand here. Okay, so now we can evaluate that integral. Okay, so you just take it term by term. Okay, evaluate the integrals of those, and we will get to our next step here. So keep our constants out here. And then we have our evaluated integrals. So again, you can pause whenever and validate for yourself that you end up in the same spot. Okay, and then all of those, remember, we want to evaluate at our limits. So we want to evaluate those from 0 to a. All right, so then getting there. We end up with a little bit nicer situation here. Hopefully this is bringing back some fond memories of years ago. Don't forget your basic skills. Okay, so now we have an expression that has eliminated all of our x's. Okay, so now we can start simplifying a little bit. So the first thing we want to do is to find a common denominator for all of these terms that will make things better for us. So hopefully you can remind yourselves how to determine your common denominator, but that common denominator is going to be 105. Okay, so then you would end up with all of your constants times your expression that you end up with when you put in your common denominator. Okay, so you will end up with 2 over 105 times a to the 7 once you evaluate all of this beautifulness. Okay, so we'll just simplify ourselves a little bit. So those 2's are going to go away. We're going to end up with a squared on the bottom, and then that will cancel to give us a 6. And so then we end up with 6 h bar squared over ma squared. Okay, oops, and there's a negative. That was a negative in there. That's where our negatives cancel. So all comes out well with our world. Okay, so that was the end result that we were looking for. So 6h bar squared over ma squared. 6h squared over ma squared. All right, so that works. So that's sort of the long and windy road version. And I will just quickly show you one other version that invokes the use of an integral table. All right, so let's go back to this point in our solution. So we'll just do method 2. And this will be our integral table version. Okay, so if you have access to an integral table, what you'll want to do is to see if you can find an integral that matches up the form of this function. Okay, so you could, again, leave this factored and combine them. Your exponents will change. I'm just going to leave this evaluated. You can evaluate those integrals pretty easily. Okay, so hopefully when you look at your integral table, you will find the following expression. All right, so your job is just going to be to figure out what all of the letters are going to correspond to for your particular expression. All right, so oops, that's an N. So all these gammas, so for those of you who are still learning your Greek alphabet, these are capital gammas, okay, these little hangman symbols, okay. We've got pitchforks and hangmen. We've got all kinds of fun stuff going on here. Okay, so that gamma term just means that you're going to do this. So you're just going to evaluate n minus 1 factorial. Okay, so whatever is down here, plug that in here, and take the factorial. Okay, so why don't you maybe take a minute and pause the video and see if you can match up your values for A and B with your expression up here, and see where you get with implementing that solution. Okay, so hopefully you were successful and ended up with something looking a little bit like this. So this is just, again, taking our coefficients here. Remember, don't forget that those are still there. Sorry, not our coefficients, our terms in here, and then multiplying them by the result that you get for evaluating the integral for this part of your expression. Okay, so these initial terms up here are essentially coming from this part, and then all of our factorials are coming from using our integral table for that part. Okay, and then don't forget you evaluated once again from your limits 0 to a here, so that's where our x's again disappeared and got subbed in with an a. All right, so then you just keep on trucking. So evaluate your factorials, simplify everything, and you should get to the same result we had previously of 6 h bar squared over ma squared. Okay, so once again, multiple ways that you can approach these problems. Okay, so you can either do everything by hand, go search out an integral table. Sometimes you will have to do the integral table version. There's just no way around that. But hopefully you can appreciate that you have the ability to solve some pretty complex equations by hand. Okay, so I know that the art of doing these types of calculations is going by the wayside with the advent of all of our powerful computers, but I still think it's a valuable exercise to go through this process for yourself so that you understand exactly what your computer program is doing. Okay, so you could plug all of this into something like Mathematica and get you'd be able to keep it in your symbolic form here. Python really only gives you numerical answers, so you'd have to plug in some values there. But there are many approaches to solving these, but I really want you to be able to approach these with the calculus. Okay, I think that's still a really valuable skill to keep honed. So I'm going to keep assigning them. All right, so hopefully that wasn't too terrible of a process for you, and hopefully this helped to kind of jog your memory of how to approach these types of problems if you are feeling a little bit rusty on some of your calculus, and then just sort of going through all the evaluations, the algebraic evaluations. I know it's been a while since you've done these for some of you, so hopefully you found this example helpful. All right, have fun, and thank you.